Hi everyone, welcome to this webinar on the foundations of causal inference and its impacts on machine learning. My name is Emre Kıcıman. I'm a senior principal researcher at Microsoft Research in Redmond, and I'll be speaking to you today together with Amit Sharma, who's a researcher at MSR India. We're both part of a group of researchers at Microsoft interested in causal inference and causal machine learning. And that will be our topic today. In this webinar, we're going to talk about why causal inference is important, what we believe is special about it. We'll walk you through 4 steps of causal inference and give you a detailed walkthrough of these steps with the DoWhy Python library. Finally, we're going to close with some of the more fundamental connections between causality and what are core machine learning challenges. So, why is causal inference important? We're motivated, and I'm certainly motivated, by this trend of computing becoming more and more integrated into so many parts of our society, with data-driven decision-making really transforming the way that we make decisions in the context of health and medicine, industry, retail, and many other scenarios. If I think about medical scenarios like whether an image of a skin lesion seems to be cancerous, if I think about how people's behaviors will change if I raise or lower retail prices, if I think about what are the implications of agricultural decisions like what cover crops to plant or when to irrigate. These are all questions that are benefiting from this trend towards more data-driven decision-making enabled by the advances in computing that have been happening over the last decades. And when we think about how to take that data and turn it into decisions, we often think about machine learning. And what machine learning at its heart is doing is searching for patterns in this data and using it to pull out insights that we can use to gain a better handle over what decisions we want to make and what will help us in all of these various domains. The problem is that often these patterns that correlational machine learning finds are spurious ones. The problem with machine learning algorithms finding these spurious patterns is that these patterns are not robust. Machine learning fundamentally makes an assumption that the data it sees in training is representative of the data that's being used, the test data where it's being used and deployed. And when that assumption is broken, machine learning makes mistakes. So, for example, algorithms that work really well at reading handwriting, recognizing objects, answering questions about images, all start to fail when the data that they're being deployed on changes. And we see that here where digits are being analyzed at different angles, where stop signs are being looked at from different angles, where the questions that are being asked and answered, trying to be answered through an image, are slightly tweaked from the type of questions that were being asked otherwise. And this can lead to some serious problems in bad decision making. For example, importantly, it can lead to biases in machine learning models in really critical situations. And so, what happens and why do we really care about this in decision making scenarios? Well, it turns out that when we start to use machine learning algorithms for decision making, we're not only assuming that the environment isn't going to change, we're at the same time, because of the decision we're taking, the action we're going to make, we're actually actively changing the environment in a way that often breaks those patterns. So, for example, think about a simple task of learning a machine learning model that will help us make irrigation decisions in a farm. Let's say we're going to be learning a model to predict soil moisture levels based on current readings and future weather patterns. We can train these models on years of sensor data from real farms and then ask the question, hey, here's the status of my farm right now, and I know it's going to be hot in a couple of days. Do I need to water my fields to make sure that the soil is moist enough? The model, trained on years of data, is very likely to say no. The soil moisture will be high when the temperature gets really high. Don't worry about it. And why might this model do this? It doesn't make sense to me, right? If it's going to be really hot, that's going to dry out the soil. Well, maybe this model learned that in the past, high temperatures were associated with high soil moisture levels because the farmer in the past has always watered on those hot days. And when we're coming about now and asking what's going to happen, that was a pattern that the machine learning model picked up on, but it's a pattern that we're going to break when we look at this result and decide not to irrigate based on the model's prediction. So if we look at this together, we're seeing computing helping with decision making in a broader set of scenarios, and we see this potential challenge where conventional machine learning patterns aren't up to the task of helping us make good decisions. The interventions that we make based on these analyses break the correlations that these machine learning algorithms depend on. And when we look into their internals for insight, we often find that they don't actually necessarily represent the models don't give us insight into how we actually might want to act in the first place. So for decision making, we need something a little different. We need to find the features that both cause the outcome, and we need to be able to estimate how that outcome would change if the features are changed. So one way to think about this is that, in supervised machine learning, we're assuming that the training data matches the test data, and we have great ways of estimating and evaluating a prediction model and making sure that we're right under these assumptions. Causal inference is really a different task, though in some ways it looks like a similar setup. Here we're not assuming that the training data is the same as the test data, and instead of trying to simply predict the value, what we're actually trying to do is uncover the underlying generative model, the values of the causal mechanisms that are creating our observed data. Now this is a good time to step back for a moment and ask, what is causation? Now this is a tremendously philosophical question. We're going to take a bit of a practical definition just to be able to move forward and make progress on some of these important problems. We're going to say that some action or treatment or decision T causes an outcome Y that we care about if and only if changing that value of that feature T leads to a change in Y, while everything else is constant. Now, what that means is we're going to have some real-world data where we actively take action and change T. And we're going to be we're going to say that T causes the change in Y if Y would have been different in some counterfactual world where we did not set T to that value. And the causal effect then, if there is a causal relationship, the causal effect is going to be the magnitude by which the outcome changes every time T changes by a unit. So we're going to estimate this value. Now, this leads us to two really interesting fundamental challenges. One is that we never actually observe this counterfactual world. We get to see what we did, but if we're really serious about that assumption that all other things being equal, we never get to see the counterfactual world where we did something different. So this leads us to the first challenge for causal inference, where we can't directly calculate the causal effect, say, for ground truth validation. We have to always be estimating the counterfactual. If we do one thing, we have to estimate what would have happened otherwise. If we do the other thing, we have to estimate, what would have happened on the other hand. And this means that there are, among other things, going to be challenges in validating our methods. The second interesting fundamental challenge is that there are multiple causal mechanisms that can be fit to any data distribution that we actually observe. not going to go too much into detail about why this is or how, but just suffice it to say that data alone is not enough for causal inference. We need domain knowledge and assumptions to disambiguate the potential mechanisms that could be causing the observations that we see. So this is going to be two of the challenges that we're going to be talking about as we go through this presentation. So just to highlight here that in the context of these decision-making tasks, there are a lot of data science and scientific questions that are really at heart causal questions. When we're doing an A/B experiment, that's one way of answering a causal question. If I change this algorithm, will it lead to, for example, a higher success rate in whatever optimization metric I'm looking at? If I'm thinking about policy decisions, I might want to estimate the impact of that policy change. Once I've deployed a policy and I want to know whether, in hindsight, that policy helped or hurt, given everything that else has happened since I deployed that policy. Now that's a very interesting counterfactual question where I'm combining my knowledge of how the policy works with my observations of the world the extra information that I've learned since. And there's fun problems in credit attribution. Are people buying things because of the recommendation algorithm I just deployed? Would they have bought anyway? Whenever I see some outcome that I care about, can I tell where that came from? So if I was to recap why we care about causal inference, it comes down to the fact that decision making in all these important scenarios depends on understanding the effects of decisions and actions. If we really want to optimize how we make decisions, we need to be thinking causally. The predictions from correlational machine learning are insufficient because of the fact that our decisions and actions are changing the correlations that machine learning depends on. Causal inference addresses this challenge directly, but does run into new challenges we have to overcome. Primarily, we have to start bringing in outside knowledge to augment our observed data. We talk about these being model assumptions that we have to explicitly augment. And we need new methods for validation and new methods for estimating those counterfactual scenarios so that we can really know that we're making progress and trust our results. So in the second part of the talk, we're going to go through the 4 key steps of causal inference. So the 4 key steps of causal inference that we're going to go over are, first, how we model our problem. This is going to be about creating a causal graph that encodes the assumptions that we're bringing in from our domain knowledge and our knowledge about how the world works to augment the data that we're using. The second step is identification. Here we're going to be taking those assumptions, that causal graph and model, and using it to formulate what we need to estimate. The third step is to actually compute the estimate. Given all the realities of the data sets, what's the best way to trade off the bias and variance for whatever task we're trying to do to get a causal estimate of what is the impact of doing one thing versus another on the outcomes we care about. And the fourth step is to validate our assumptions and run a number of sensitivity analyses to really see if we can refute this estimate, see if we can come up with a reason not to trust it. And this comes back to those challenges around the lack of ground truth validation for many of our tasks, which means that we have to find new ways of making sure that our analyses are trustworthy. To implement these 4 steps, we built DoWhy. It's an open source Python library for causal inference. Our motivation for DoWhy was really based on our experience working with data scientists and others on causal inference. And we noticed that the most challenging parts of the causal inference process wasn't the statistical estimation, but actually the initial encoding of model assumptions in the form of a causal model, and the last step of validating and refuting the results at the end. These were 2 new steps that are different from what we do in conventional machine learning, and so this is where we thought people could use more assistance. And that's what DoWhy does. It really steps people through these 4 steps in a way that ensures that people are making a transparent declaration of their assumptions and helps them evaluate those assumptions and the results that they're getting at the end of the analysis as much as is theoretically as much as is possible. So these 4 key steps are going to be the framing that we use for the rest of this part. We'll start with modeling our assumptions. Modeling and capturing our assumptions is about converting domain knowledge, our intuition, and concrete knowledge about how the world works, how the particular system we're analyzing works, into a formal model that we can use to augment our data. So a good model is built around exposing the key causal relationships between the outcome that we're analyzing and the other variables that might influence it, including the actions that we're trying to take. The assumptions are about how different variables affect each other, and we usually encode this as a causal graph, where each edge encodes a mechanism. A direct edge is from one node to another, from A to B in this case, is a direct cause, where the value of A influences the value of B. The graph itself now in total implies a number of conditional statistical independencies. For example, in this case, A and C are independent of each other. And D is independent of A, conditioned on B. You can read these statistical independencies off the graph using rules that are called D-separation rules. We won't get into that, but it's a fascinating topic if you want to dive deeper into it. The key intuition about these causal graphs is that the assumptions themselves actually aren't the edges. The assumptions are encoded by the missing edges and the direction of the edges. The way to think about this is as follows. If I draw an arrow between 2 nodes, A and B, what that says is that when A changes, B's value is going to change, weighted in some way. But that weight could be 0. So really drawing an edge between 2 nodes isn't assuming anything. It assumes that there might be a relationship. But if I remove that edge, then I'm setting that weight to 0 by definition, and I'm saying that no matter how I change A, without some path between A and B, B's value is not going to change. These relationships that we're encoding in this graph also represent stable and independent mechanisms. That is, if we have a large causal graph that is representing a bunch of different stuff in some system or environment, we can expect that if we reach in and change the system in some way, we change some of those arrows, we can assume that the rest of the system, the rest of the causal graph, is not going to be affected. Another key intuition is that the graph actually can't be learned from data alone. While we can look at the data and learn something about what the shape of the graph might look like, it turns out that the same data can be represented by multiple graphs. We can narrow it down and get to some equivalence class, but we're not going to be able to find the right one. And that's why we need to encode this our domain knowledge explicitly, because we can't just skip this step and figure it out later. And finally, it's important to note that these graphs are a tool to help us reason about a specific problem. We can write these graphs at different layers of abstraction, at a high level, at a very detailed level. We can capture major causal relationships or the most minor ones. And the right answer and the right way to model these causal relationships is going to depend on the questions that we're caring about and basically the context of the specific problem. Here's an example graph just to dive a little bit into the interpretation of these graphs. Here we're looking at a graph that shows some of the relationships between user interest, user fatigue, what people have done in the past, and then some anonymous treatment here that we're considering. We won't say what it is, and some outcome variable. Reading this, we can read off what we're doing in terms of what our assumptions are and the underlying system. We see by the fact that there's no arrow from user fatigue to user interests, and there's no path that we can follow along these directed edges. to go from user fatigue to user interest, that user fatigue does not affect user interests. We can change the values of user fatigue. We can, maybe find ways of making sure our users get more sleep or get more rest, or walk away from the system we're building, and feel more relaxed. And we will not be affecting their interests. We see also that past clicks does not directly past clicks, or the history of what a user has done, does not directly, according to this graph, affect the outcome that we care about, this Y. It does, however, indirectly affect it through its influence over whether or not people see the treatment that we're studying, and so on. Now, when we are thinking about going in and changing the value of this treatment feature t, note that in this example graph, we see that t is being influenced by quite a few things. But when we talk about wanting to go in and set t or change t, what we're really saying is that we're going to build a new system where the treatment t is not influenced by these other variables. It's just simply influenced by whatever we decide to do. We're going to reach in and change t potentially completely independent of what's going on in the rest of the system. So now this is actually a new intervention graph. It's basically a new system where all edges that were going to t have been removed. Now this represents a new data distribution. We usually refer to this distribution using do of t, so this operator. And the causal effect that we want to capture in our analyses in causal inference is basically the distribution of y, the probability of y given do of t, given that we are setting the value t to setting the feature t to some value. And now this leads directly to now the identification problem, the identification step of causal inference. Here what we're going to do is we're going to take that p of y given do of t, and we're going to try and figure out how we can calculate that value. So the challenge here is that our observed data is generated by the graph on the left, where t is being influenced by everything else going on in the system, and those things are also influencing the outcome that we're observing. And we want to answer questions about this intervention graph where t is being set by us independently of everything else. And so now the question is, how do we represent quantities from the right-hand graph, p of y given do of t, using only the statistical observations that are in the data generated from the left-hand graph? Now, there's a trivial example, a solution to this in the case of randomized experiments. In randomized experiments, the value of t is being set with a coin flip. It is statistically independent of everything else, so there are no edges from the rest of the system to t in the first place. This means that our observed graph is the same as the intervention graph in a randomized experiment. And what this means is that the probability of y given do of t is equal to the observed distribution of p of y given t. And this leads us to kind of our intuition for one approach to doing causal identification. It's going to be basically, can we generalize this insight about randomized experiments by taking our observed data and trying to find ways to tweak it to simulate a randomized experiment. So when treatment t is caused by other features, z, for example, we'll call it a set of features z, we're going to try and adjust for their influence to simulate a randomized experiment. Now this approach is called the adjustment formula, and the adjustment formula you can see on the screen is basically adjusting for all the observed values of these features z that are influencing the treatment. Now the feature z can't just be any set of features. They have to be of what's called a valid adjustment set in order for this formula to give us a correct estimate of the causal effect of changing t on the value of y. There's a couple of different valid adjustment sets. One is all of the parents of t. If you set z to be all the parents of t, then this formula will give you the right answer. You can also identify a set of features using what's called the backdoor criterion and the towards necessity criterion. And the the key intuition, we're not going to define these algorithms, but there are algorithmic approaches to identifying these features. The key intuition is that the union of all features is not necessarily a valid adjustment set. You just can't go and use all of your data to do this. You will get incorrect estimates. Um, and I just want to point out, you might be thinking, why don't we just always use the set of all parents of T? Why do we need more complicated ways to identify valid adjustment sets? Well, the issue is that sometimes these parent features, even though we know they exist, they might be unobserved in our data set. So we might know that they're there, that they are influencing the value of T, but for one reason or another, we might not have been able to measure them. We might not have captured them in our data set, which means that we have to find alternate adjustment sets that don't include those unobserved variables. In addition to adjustment sets, there are many other identification methods. There are identification methods that rely solely on the shape of the graphical of the causal graph. These are, in addition to adjustment sets, there's the front door criterion, and there's randomized and natural experiments. And then there's also other identification methods that, in addition to the causal graph, require some additional constraints or assumptions about the shape of causal relationships or or narrow down on the kind of causal estimate that we're interested in identifying. These include instrumental variables, regression discontinuities, and differences. And many of these methods can be used through are already in DoWhy. At this point, I'm going to hand off the presentation to Amit Sharma. As I mentioned earlier, Amit Sharma is a researcher at MSR India. He's a co-developer of the DoWhy Python library, and he'll step us through the rest of the 4 steps of causal inference, starting from estimation, and into the final part of the talk on the connections between causal analyses and core problems in machine learning. Thanks very much.
Thank you, Emre. I'm Amit Sharma, and I'm excited to present this webinar. Let's move to the estimation section now. Emre just talked about the first 2 steps of modeling and identification. And once you have the identified estimand, we would want to use the observed data to compute the target probability expression. For common identification strategies using adjustment sets, the estimation really just boils down to conditional probability estimation. So here, for example, I'm just showing you that the do operator converts to a probability distribution of y conditioned on t and w. And of course, this is assuming that the adjustment set is a valid adjustment set. In binary treatment case, the thing becomes even more simpler. So if you want to estimate the causal effect, it's simply a subtraction between the conditional distribution at t equal to 1 and the conditional distribution at t equal to 0. And so in all the estimation steps and all the estimation methods that you may find, the final goal is that we want to estimate the conditional probability, and you want to keep the confounders constant. How do we do that? Let's start with one of the most simplest methods known, which is just matching. So imagine that you have data about health, and you have people who were given a treatment, which meant they did cycle. And then there were other people who did not cycle, and your goal is to find the effect of cycling on their health, right? So we have these different people here. What the simple matching method says is that let's just match people who have the same baseline health and confounders together. So you match children with each other, you match people with different characteristics, which are shown by colors here. And once you do that, you have effectively created a set where the confounders are the same between each pair. And so therefore, when you just compare their outcomes, you are guaranteed to get the causal effect. And so as I share here, of course, in practice, you won't have exact matches. There might be high dimensional data. And so typically we have a distance metric as defined here. And we say that a matching condition is that the distance metric should be lower than a certain value epsilon. Now this can work really well if you have a small number of confounders. For example, the equation here, just you have to subtract the outcomes for each match. But in practice, you will have many people who would not be matched. They are shown in the bottom gray box here. So these are people for which we are unable to match anyone, and therefore we have to exclude them from the data. And as you can see, this simple method actually shows the challenges of building a good estimator, especially in high dimensional data. If you think about it, we removed all these people because we could not match them. And that just meant that we had a very stringent matching criteria. And that means that our estimate will not be reliable because we just have a small matches that we have to rely on. On the other hand, if you think you can just relax the matching criterion and obtain many more matches, now the problem is your estimator is biased. Because it's no longer capturing the do operator that you wanted, it's just not being able to keep the confounders constant. And in the real world, things become even more complicated because often you might just have a small set of people who have been given the treatment, in this case, cycling. And so what will happen is that those few people won't be matched as much, and it will lead to both high variance and high bias. And so what has happened over the past decade is that people have realized that we need better methods to navigate this bias variance trade-off. And I'll just talk about two examples of recent machine learning methods that have come up that can help us in this estimation problem. So the question I want you all to think about is, let's say you tried to match a person or a data point and a good match does not exist. Is it possible to just create a synthetic match? Let me describe what I mean by it. Let's say on the right-hand side, you're seeing a graph about people. The orange people are the people who are the treated people, and blue are the ones who did not get treatment, right? So if you just try the simple matching strategy, as the vertical lines show, you would find that there's no one else in the blue case who had an equal value of the confounder to the person that I'm pointing to using the vertical arrow in the orange bar. And similarly, for the people who are in control, if you just pick one point at random and see which person has the same confounder, you would not find anybody. And so what machine learning can help us do is we can actually estimate the function of the outcome for different treatment values. So that's what we do here. So we say, let's take all the people who are treated and try to find the relationship of W, the confounders, with Y. And in this case, it's a straight line. And we can do the same thing for the control group as well. What does this give us? This gives us now a pretty good matching for any person in treatment or control. So for example, for the blue bar here, instead of matching to a real person, I can just match to the prediction that our model gives. And again, we have to always make sure that the function that we are estimating is a good function approximator, because the key assumption here is that the F that we estimate now captures the true relationship between the confounders and outcome. If that is true, then the causal effect again can be given by simply sort of differencing the outcomes of the treated and the control while they are matched with the same confounder. And as you can see, other machine learning methods can generalize estimation to harder problems as well. I'll give an example of continuous treatments. So this has been a hard problem in causal inference for many years, where it's pretty easy to do if you have treatment equal to 1 and treatment equal to 0, binary. But what do you do when your treatment can be continuous? So this is one method that has been recently proposed, which takes the cue that, of course, as we discussed earlier, just having a predictor is not enough. So you can't just take all your data, you take treatment, you take confounders, and just say, I'm going to build a predictive model. That's not the right approach. But there's a simple trick that you can use to still be able to use predictive models. So what we do is that we break down our task into two subtasks. Let's look at the graph first. We can always come back to the equations. So what the graph is showing is that typically Y, the outcome, is having some correlation with the confounder, and that's why you see a tilted line there. And similarly, the treatment can also have some correlation. And this is the issue. We want to remove this correlation so that we can actually capture the effect of T and Y. So what the double ML method says is that let's build a predictor using W and try to predict Y. And similarly, let's build a predictor using W and try to predict T. Once we do that, what's nice is that whatever is the residual left, it's literally the amount of variation in Y that is not explained by W. And so it is the unconfounded variation that we want to look for in Y. And so that's what this method does. In the first step, we take the gray dots that we have for the outcome. These are static in the graph, which means they're independent of the confounder. Similarly, we get an independent residual for the treatment. And now causal inference just becomes a simple regression of these residuals on each other. So what we have done really is that we've used machine learning to extract out the confounded factors of both the outcome and the treatment. And once we have those residuals, we just use linear regression or a simple method to find out the causal effect of T on Y. And depending on the dataset properties, actually different estimation methods can be used. So for example, we talked about matching, we also talked about double ML, but actually there are many different methods and you have to try them and see based on your dataset which one works. The good news is that all these methods are implemented in DoWhy, either directly or through a library from Microsoft, which is EconML. And so these all methods, which are pretty complicated, are now available in a simple library for you to use with. But that's not enough, right? So now we have our estimate. That's great. But can you call it a causal estimate? Well, as you probably remember from the earlier parts that Emre presented, causal inference really depends on the assumptions, right? So just having an estimate from a causal method is not enough. Now's our chance to check whether the assumptions are actually being valid in the current setup. And just as a recap, we have assumptions which are pretty much untestable for most cases, going through all the three steps that we so far discussed. So the first step, we discussed model. There's an assumption about which edges should be there or not. Maybe we made a mistake. There's also an assumption about whether we missed any unobserved variable that could be confounding our estimate. In identification, there can be assumptions about some parametric assumption that we made about deriving the estimand, or some other kind of assumption in the graph that we now have to be careful with whether it actually is valid in the data or not. And similarly in estimation, as you just saw, we made assumptions about the functional form. We also made some assumptions that might lead to high variance in the estimate. And so this is quite important. It's probably, to me, one of the most important steps of causal inference, because unlike in machine learning, where you have cross-validation, there's no such data set, no such gold test data set available, right? So we really have to now get creative and think of how can we check the robustness of this estimate? Well, the best practice from experts is that try to do as many robustness or refutation tests as possible so that you can rule out violations of assumptions. So we have typically two types of tests you can think from a software development perspective. One is the unit test, which just tests one part of your analysis pipeline. So for example, you can just test whether the modeling is correct using a conditional independence test. Similarly, you can test identification using deseparation and so on. And separately, we have what you can call integration tests, which just test whether your whole process is correct or not, right? So they just begin with an assumption about what a correct process should do and just test whether your method is following that. And we'll discuss one or two of these. We'll specifically discuss the placebo treatment refuter and the sensitivity analysis. Again, we won't have time to discuss all of these methods, but they are all implemented in DoWhy, the library that we have built. And so you can all, for any kind of estimation, well, now it's very easy to just run all these tests at once and check these assumptions. One caveat I'll say before we begin is that these tests are not proofs. They're not able to tell you whether your analysis is correct or not. Think of them more like they can weed out the bad analysis very quickly, right? So they can tell you when a method is wrong, but they cannot actually, it doesn't mean if all tests pass that the method is correct. It just means that it's not really bad. And so you've made all the due diligence in your analysis. Okay, so I'll describe sort of three methods just to give an intuition on how refutation works. And you can think of it almost like the scientific process. You have an estimate now, you have a theory, and you want to check and you want to falsify it. So if you have a problem with your modeling and you're concerned that you might have missed some confounding or you might have missed some other variable, one easy thing we can do is that we use the knowledge of causal graphs properties. So we know that every causal graph implies certain conditional independence constraints on its nodes. Let's take an example. So the graph on the right, you can see that there's a treatment, there's an outcome, but the user has said that there are other variables A and B, which are affecting the confounder. So just by looking at this graph, we can actually deduce, this is analytically, that A should be independent of B, That's the assertion in the graph. Similarly, A should be independent of T, the treatment, given W, and B should be independent of T given W as well. Now that's pretty nice because the user has said, here are the independences I believe exist in my data. And the refutation method can say, sure, let me check them. I have the data with me. Let me just check if these are correct or not. And that's exactly what this method does. So it says that let's check if the observed data satisfies the independence conditions. And for this, we implement an appropriate statistical test. If all the conditional independences pass, great. If not, then it means that we have to look at our model again and maybe change some arrows or make it more complex. Once you're not so much worried about your model, you might be worried about other things down in the steps that might have gone wrong, right? So you might be worried about maybe there's some problem with the estimation or identification, and that's where integration tests help. So one example is a placebo treatment. All we are saying here is that we don't know what happened among the modeling assumptions and the identification assumptions, but here's something that we can attest to, and which is that if the treatment is something that is completely random, then it should have no effect on the outcome, right? And that's just a simple assertion. And we can say that if given such a data set, any causal inference method should return an estimate of 0. And that's exactly what we do. If you look at the graph on your right, the first one is the true data, and the second one is a simulated data where what we do is that we look at the treatment column, remove it from the data, and replace it with a completely simulated uniformly random variable. So for example, you can choose Gaussian. So now because you generated this variable by yourself, you know that it cannot be causing the outcome, and so the effect has to be 0. And then we can just rerun our whole pipeline, check whether with this reduced treatment, do we still get the estimate actually equal to 0. And again, if it passes, great. If it doesn't, then the method is incorrect and we have to make amends. And the final one I'll talk about is the most interesting in many ways, which is that we can now test how our method would be sensitive to unobserved confounding, right? So remember, this is one of the hardest sort of assumptions in causal inference. We can never be sure whether in our modeling there was one effect or one variable that was missing. And so what we can do is that we can say, sure, let's try to simulate a variable. Let's try to simulate a confounder with some correlation with both treatment and outcome. And now let's rerun our analysis again and see how much our estimate changes. So this method typically doesn't give you a yes/no answer, but it gives you a sense of how robust you are to even a small confounder that might have gone missing in your data. And this can give you a subjective understanding of whether the estimate can be trusted or not. Now, armed with these 4 steps, let's just walk through how you can do them using the DoWhy library that we talked about. It'll just give you a good sense of how this causal inference analysis happens in practice. Just to make things fun, we have actually created a mystery problem. This is available online. I'll present the link later. Imagine that you are a data analyst and someone just gives you a data set, and this is how it looks like. Over time, X and Y seem to be reasonably correlated. And if you look at the data, you have 3 variables, X, Y, and W. So what do we do? So in DoWhy, the first step is to model the problem first. So before even thinking about what you're going to estimate, let's try to model this whole setup here. So that's what you do using the causal model class, as I've shown here. And you specify what variable is the treatment outcome. You can also specify a graph here. And then DoWhy says, great, we have recorded this model. And if you ask it to present it, it can present it as a graph. So here, there's a sort of a familiar graph where we have a treatment outcome and some unobserved confounders. Second step now is that given the graph, now everything else is automatic in DoWhy. The graph is where really human knowledge and human judgment goes in. After that, we just say, hey, you have the model, let's identify the effect. So that's the second line of the API. And if you see something interesting is happening in the outcome that comes from DoWhy. One thing is that it shows you a warning. It tells you that, hey, this is observed data, not from a randomized experiment. There might always be some missing confounding. And so this is a way of reminding the user again that they have to be careful and recheck their model in case something is missing. But if not, then it gives you automatically the exact estimand to estimate based on the model given to you, right? So it's basically implementing do calculus for you so that you can simply give the graph and you immediately know what to estimate. Once you know what to estimate, now you can say estimate effect. So that's the third part of our API. You say the same model, estimate effect. And in this case, we're using linear regression. But as I said, you can use sort of multiple methods of different complexity. And so now DoWhy actually does the estimation and comes up with the estimate of 1. Now what this means is that changing the treatment value by 1 unit would also change the outcome by the same 1 unit. What's interesting is that if you just look here, the causal effect is different from the observed data. It's actually a lower effect than what you would have if you just believed the correlation. And finally, the most important step is to now check whether we are actually having a robust estimator or not. Here I just show one refuter. We chose the placebo treatment refuter. Remember, the placebo treatment just replaces the treatment with a placebo. So our goal here is to check whether the effect now goes to 0 or not. As you see in the output, the effect does go to 0, not significantly different. And so now we can feel reasonably confident that our model is a good one and we can trust the estimate. In fact, because it's a simulated data set, we can also check here, which we can't do in real world. And we actually find that the effect is the same. You can also try out this whole example on GitHub. It has many more details that you can check out at the link below. Our goal here was to simply give you a breeze run through how DoWhy works and how causal inference can be made practical through the 4 steps. In practice, actually, DoWhy is actually much more extensible API. Our goal is not just to implement the 4 steps, but also allow external implementations for those 4 steps, but they still follow the same 4-step API. So for example, we are now already supporting estimation methods from external libraries like econML and CausalML. The only difference to a user would be that instead of saying backdoor.dowhy, here they can say backdoor.econML. And we also have external contributions. So for example, Adam Kelleher, we're very thankful to him. He's added a pandas data frame extension, which means that now you can estimate causal effects using the same pandas API as you would work with a data frame. So in summary, we've created an end-to-end library for causal inference, and you can answer what-if questions and estimate causal effects of any variable. Importantly, using data and domain assumptions. You need both. And the 4 steps are repeated again here. I would just repeat the most important ones, which is we have a formal framework to make assumptions explicit, and we provide a set of automated tests to check robustness of the estimate. Let's pause for a second and think of what we've achieved so far. We started with a problem that machine learning is powered by correlations, and then we discovered that causal inference is a great framework that can help us make sense of the data and find out the causal effects of any variable we're interested in. And so that's where we are. But actually, in the last 5 or 6 years, there's been another set of work going on that's even more interesting in some sense. So what's happening is that we are realizing that we can use causal inference to also improve machine learning, right? So it's not just that machine learning methods can be used for high dimensional causal inference. Actually, causal inference can be used for machine learning, and that's really exciting. So what I'll talk about is just give a view into this recent research. A lot of it is active, and we'll see how causal models can be more generalizable. They can have better privacy guarantees. And they also give you a very principled framework for thinking about responsible machine learning. All right, let's get into it. So what is causal learning? So if you're familiar with standard machine learning, we are typically given a data set, and our goal is to predict y as a function of x. And what we do is that even though you might have some information sometimes, for example, on the right, I'm showing you a graph. people don't use that, and they just say that just minimize the loss of a function of x to y. Causal learning says that that's not enough. To truly build generalizable models, let's use the knowledge that we have about our variables. So in this case, we say that the graph shows us that only xc are the set of variables that are causing y, because they are the parents in the graph. All the others are simply correlated or blocked by xc. So what causal learning says is that let's just build a model only on the xc variables. In most cases, actually, we have to learn the representation of xc. It's not like xc is given to us. And so therefore, causal ML problem becomes the problem of learning a causal feature representation. As I'll show, it can have lower train accuracy at some points, but it does stay consistent with new domains. And so these are the three benefits that you get if you can build a model that only depends on the causes. The first benefit is that the out of distribution error of causal models is lower in the worst case. The intuition is simple. If you have a graph like this, imagine that you move to a different domain, right? So you may have an intervention that means that the distribution of data might change, the distribution of features might change, and that's what is being shown by the hammers here. But the best part about causal features is that across all these interventions, the function that connects the causal features to the outcome stays the same. And so if you have a model that sort of is predicting disease in one hospital, it's going to be the same as you move it to other hospitals as well. The second property that we get is that it also has stronger differential privacy guarantees than associational models. This is a slightly technical result, but just to give the intuition, a causal model, because it's focusing on the common invariant relationships, it doesn't really care about the individual specific relationships, right? So the extent to which you can use the predictions from a causal model to identify back some individuals in the data has to be low. And what we show is that in practice, the differential privacy guarantee is always stronger for a causal model compared to a machine learning model. And finally, just because of differential privacy benefits, we are also able to show that causal models are more robust to privacy attacks, like membership inference. So in membership inference, what happens is just by knowing the output of a machine learning model, just by knowing the logits, for example, you can predict whether a particular person was in the training data of a machine learning model or not. And just sort of very intuitively, this happens because sometimes machine learning models overfit to the data, and so their predictions hold information about the training set. And since we are better in causal modeling with differential privacy, it turns out the models are also more robust to privacy attacks. Now, how to build causal predictive models is a really exciting area of research. And this is something that our group at Microsoft also works in. There are three main ways that have come up. One is use multiple domains and the diversity in those domains. The other is to use some randomized experiment data. And the final one is to use causal constraints, so domain knowledge that people would have. And we are very excited to see what more comes up in the future for building these models that also generalize well. And just finally, I want to end with showing that causal reasoning also provides useful definitions of responsible AI concepts like explanation and fairness. So imagine that the typical example of explanation is that you applied for a loan, but you were denied. What happens typically is that you may have a feature importance explanation saying that annual income was the most important. But this gives no information to you. It doesn't tell you what you can do. And that's where causality comes in. There's been work proposing counterfactual explanations, which says explicit knowledge about if you change your income to 100,000, you would have got the loan, right? So it's really sort of telling you what you can change and giving you actionable information that can be useful. And similarly, fairness also can be explored from a causal angle. The simple idea is that if you can find counterfactual explanations for a model using only sensitive attributes like gender, most likely there's a problem with the classifier, and there's a formal definition of it in Kushner et al. And I give you a simple example that if you find a person gets rejected while just changing the gender, that's a problem with the model, and you can extend it using more formal counterfactual definitions. So in summary, causal reasoning can help us enable better generalization better privacy, and more responsible ML models. So there's a lot of interesting work still to be done in this area. Just to conclude, we hope that during this session, we were able to communicate that causal inference is key to many decision-making tasks. We can capture what-if scenarios that are not captured by traditional ML. But more importantly, it's also harder, right? So there's no free lunch. We have to model assumptions well, and we also have to be careful to validate them. More excitingly, I think there's interesting exchange between conventional ML and causal ML, like we just talked about. And this is a very exciting area that we are contributing to as well. We also want to make these resources more available and more accessible to a broader computer science community. So that's why we are starting to write a book. We've written a few chapters on causal machine learning that is publicly available on the link here. And of course, we also have our DoWhy library that we would love if you can check out. And also, if you're interested in our publications, you can check out the publications of our Causal ML group at this link below. With that, I thank you. It's been a great pleasure giving this webinar. And now we look forward to your questions. So Emre and I will now be live, and we'll be taking questions.
Hi, everyone. Thanks for attending the Foundations of Causal Inference and its Impacts on Machine Learning webinar. We are now in the live Q&A session. I'm Amit Sharma, and I have with me Emre Kıcıman. And over the next 15 minutes, we are going to be answering some of the questions that you asked us through the chat. Let's get started. So our first question that we are asking is, what do you do when you don't have the causal model? And how do you actually go ahead and start constructing a causal model for a practical system? Emre, you want to answer that?
That was market research using causal inference. That's really fun.
Are we live yet?
We are live. It sounds like Emre is having some connection issues. Amit, if you want to take that one, you can go ahead.
Sure. So one of the things to understand is that we don't need the full. We don't need the full causal graph. We just need certain variables that we are interested in. So let's suppose your goal is to estimate the effect of a recommendation system where you know that there is one product that's being shown and the other product that's recommended next to it. So in that case, it's not important to know all that is happening in the recommendation system or the live system. All we need to say is that here is a product, here is a second product, and one of the biggest features that's probably impacting both of them are users' preferences for these two products, right? So as long as you have variables that speak to the user's preferences, and you have other variables which are contextual variables like time, location, and so on, you're already in a good place with respect to causal analysis, in the sense that if you assume this causal model that these variables are the confounders for you, then what you estimate will already be better than what you could have estimated by just sort of putting all the variables together in a model. So that's perhaps the first insight, that we don't really need to model the full system. I think all you need to do is, for a specific question, you just want to find the variables that are relevant to that question, and all the others can be put up as one sort of unobserved nodes or confounders. The second
Hi.
thing to note is that, hi, Emre. Do you want to answer this question? Oh, it seems like Emre is having some trouble. The last thing I would add about causal models is that it's often a dialogue in our experience with the domain experts. Whenever we start with a problem, I think as computer scientists, we often have this desire to learn as much as possible from the data. But one of the fundamental results in causal discovery is that it's not possible to uniquely determine a graph based on just observational data. So you either need to do a lot of experiments, or what we found in practice that's very useful is that we talk to the domain experts. If you're, let's say, looking at a system that is in healthcare, we can talk to doctors. If similarly for any other system, we can talk to the people who designed it or who know more about it. And I think the key insight that we want to convey today is that it's just about having the right causal model, even if it's an incomplete causal model. In practice, what you'll observe is that even with that incomplete causal model, you'll be closer to the true estimate compared to not using it. So that's another way to think about this problem, is that even with a partial model that's causal, you may get better insights than having no model at all. Let's look at the second question that came up. So this was about explanation. Actually, two of you asked this question. So there are explanation methods like Shapley values. There are also other feature importance methods. And the question is, how does causal inference and DoWhy differ from these methods? And also, how can DoWhy be used for feature importance? So the first thing is to understand that many of these feature importance methods, if you think about them and just abstract into what they're doing, they essentially say that given this input, this set of, let's say, x1, x2, x3 features, there was a particular output y hat that I observed. These methods say, let's try to imagine multiple scenarios, or now that we have this vocabulary, multiple counterfactual worlds, where these features took on some other value. And then they try to estimate on all these worlds what was the importance of a particular feature, right? So this is what methods like Shapley value do. They say that let's imagine worlds where x1 was initially 1, and then we see how much effect you get when you add x2 as well. And similarly, you can say x2 was 1 and how much effect does x1 add, right? And so there are many such methods, but the sort of key challenge they have is that they have no knowledge of what ordering is the right ordering and which combinations of variables are just impossible in the world. And I think that is what DoWhy offers here, is that if you're trying to do feature importance, or if you're trying to do explanation, in any of these methods, you can imagine having a causal graph behind it that tells you whether certain combinations are possible, not possible at all. So by domain knowledge, you would know that two features can never be one at the same time, or maybe you also know that it's always that x1 is the first feature that is activated. So the short answer is that I think there's interesting ways in which causal inference can be used for explainability, but I think one of the first ways is in just understanding that it helps us construct these set of counterfactual worlds against which you are explaining something. How it happens in practice, we have a couple of notebooks on DoWhy on GitHub. Essentially, you can think of trying to estimate the causal effect of each feature one by one on the outcome while you're conditioning for the other set of features that you have. Then there was another question about how Microsoft Research is using causal inference. So here, this has been an interesting journey for us, where we found causal inference applications in a number of places at Microsoft. So I'll talk about some of the sort of things that we started working in, and now I think the various places in which causal inference is having an impact. So where we started was questions about online networks, online recommendation systems. Emre did some great work on online social networks. Hi, Emre, are you back?
Yes, I am. Sorry about those technical difficulties. Not sure exactly what happened, but
do you want to take this? Yeah, so we were just discussing this question about how Microsoft Research is using causal inference. And I started the answer by saying that both of us started with online systems. So I think you did some work with social networks. I was working on recommendation systems. But I think now we are seeing that there are multiple applications in business and marketing, for example, sales as well, in finding out the right interventions. We are also seeing applications in traditional machine learning, sort of predictive models, and how you can make them more generalizable to new domains. And then also there are applications in sort of finding out for whom the intervention works well. So there are applications in Bing as well, and some others. Maybe Emre, you want to talk more about how we're using it?
Yes, I mean, the way I see the place where causal inference can have the most direct impact on our computing systems, and the way I abstract it out is really around decision-making systems. That the places where we're making decisions and intervening in the system as a result of a machine learning model is where we need causal methods the most. And this thinking, I think, really spans a lot of domains. We've certainly seen it in trying to understand the signals that we get from people's digital traces to help us understand what's happening in the real world in health contexts, with real-world evidence. We see it in online systems where we're studying user behavior to understand what's working and not working in our products. And we're even starting to see it in industrial contexts as well, where people are using machine learning models in more in a variety of industry, agriculture, and other settings, as well as the sales and marketing type of domains where econometrics has more conventionally used these methods. I guess one other interesting kind of place where we're doing this type of work now, Amit, is also in trying to use causal insights to improve traditional machine learning tasks as well. So how do we improve prediction and classification, for example, where we might not need necessarily a causal understanding of the underlying system, but where we believe that by using causal methods or relying on more causal features and relationships, we'll be able to improve really core machine learning attributes that we care about, like generalizability and robustness.
Yeah, that's a great point, Emre, and it actually connects well to a question that was also asked, which was that how can we understand why conventional ML methods may not work as well, and what is the secret sauce behind causal methods that make them generalize well? So I'll just give a very simple example here that can whet our intuitions here. So this is a common problem that has now been well researched, and it's an active area of research as well, which is assuming that you have two domains and you're trying to make a prediction task. So you can even imagine the simplest task in computer vision, which is MNIST, and you're trying to predict the digit based on the image you see. And it can just happen that in these two domains, in one of the domains, color is correlated with the digit. And when you just do conventional ML, it just tries to look for the simplest feature or the most sort of easy way to get to the right prediction and a high accuracy. And so in conventional ML models, they have no way to know whether color is the right feature or whether the shape is the right feature. And I think what we are seeing is that infusing some of the techniques and insights from causal inference into the prediction problem. So for example, in this case, you can develop causal regularizers to say that some features like shape are more important here. What it does is that it then gives you your predictive model as well, more generalizability to new domains. So that's just one of the simplest examples where you can think of, like when you have data from multiple domains, how do you extract the features that stay consistent over all these domains?
I think one thing that's worth emphasizing is that when traditional ML models are relying solely on the data, and so if you have spurious correlations in your data, your model won't be able to easily distinguish between the spurious and the causal relationships. And when we know the spurious ones, by definition, they might change because of some environmental difference. And what causal methods let us do is it helps us formalize our assumptions about either the structure of the data gathering process or about the fact that data came from multiple environments, and it helps us bring that knowledge into the analysis in a more systematic and rigorous way, and that provides that extra little bit of nugget to help us focus these models on the causal relationships. Where otherwise, I wouldn't say that there's anything that we're able to do with data alone with the causal method that we couldn't do with the conventional machine learning model. It's the fact that the causal analysis is bringing in an ability to reason about some additional structural or relationships among the data itself.
Yeah. So maybe we have time for one last question. I think there's a question about unobserved confounding. We obviously talked a lot about that in the presentation. And the question is, how do we account for unobserved confounders in our causal model? So maybe I can start. So there are two places in which we want to account for them. So the first place that is in the modeling itself. Often what happens is if you're doing the traditional statistical analysis or even the machine learning analysis, what happens is you look at what data is available to you, as Emre was saying, and you try to build the best estimator for your effect or for your quantity that you're interested in. The downside of this is that if your data itself does not have all the right variables or it misses some really important variable, your estimate might be off, and you would have no formal way or even no intuitive way of knowing that that is happening. So I think the first way unobserved confounders can be used, and this is what we have tried to do in DoWhy, is that you explicitly tell or state that in your causal model itself. So in your graph, for example, you can say not only that there is an unobserved confounder, I believe, that is affecting this problem, but also how is it affecting this problem, right? So is it just causing one of the variables in your model, or is it causing probably all the variables in your model or some middle ground? So I think that's one way that we account for it. And this just gives us a perspective or some humility into what the estimate that we are capturing is really capturing. So is it the causal effect or not, right? So that's number one. I think the second way that we can account for it, and this is also one of the probably the biggest strengths of DoWhy as a library, is that you can do your analysis without having access to that variable. But at the last step in the refutation, you can say that I know my analysis is not perfect because there was an unobserved confounder. Let me try to now simulate such a confounder and try to see how much my estimate changes. So this is, you can think of it like a sensitivity analysis, where what we are saying is that we don't know how big that confounding was, but we can simulate confounders of different strengths, which are unobserved, and see how much our estimate would have changed if we did include such a variable in our analysis. And looking at that, along with sort of domain knowledge of how strong a confounder could be that's missing, I think that can give us a much better idea of how robust our estimate is. and also how trustable or generalizable it may be.
Just following up on that, it turns out that even when we don't have the opportunity to observe a particular confounder, the domain experts can still have intuition about how strong that relationship might be. And if we are able to compare the strength of the unobserved confounding that's necessary to reverse our understanding of a causal relationship, what we see is that we can take a look at that strength and compare it to the strength of the confounders that we are able to see. And then a domain expert can say, yeah, doesn't make sense that there's some unobserved confounder that's thousands or millions of times stronger than anything that we've seen so far. And maybe in that case, you trust your analysis more than if even a tiny bit of confounding were to reverse your estimates.
Great. Thank you all for attending today. We really appreciate your participation and all the questions that you asked. If you're interested in learning more, we have some great resources in the resource list to the right of your screen. The list includes references to the DoWhy library on GitHub. And within that, on that library, you would find notebooks there that you can explore as case studies on how DoWhy can be used. And also there are links to book chapters that we are writing on the same topic of causality and machine learning. And you can find the first 2 chapters of our book also available in the resources. We look forward to seeing how you can build on this research and evolve the area of causality and machine learning. For any further questions, I would say we are happy. You can probably reach out to us. You can find us online. And also on the DoWhy issues page, you can raise issues, you can raise questions, and we'll be happy to answer them. With that, have a great day, and thank you so much.
Thanks, everyone.